CMOS, D-Latch and edge-triggered flip-flop. With the widespread use of CMOS circuit techniques in digital integrated circuit design, a large selection of CMOS-based sequential circuits have also gained popularity and prominence, especially in VLSI design. Throughout this chapter, we have seen examples showing that virtually all the latch and flip-flop circuits can be implemented with CMOS gates and that their design is quite straightforward. However, direct CMOS implementations of conventional circuits such as the clocked JK latch or the JK master slave flip-flop tend to require a large number of transistors. In this session, we will see that specific versions of sequential circuits built primarily with CMOS transmission gates are generally simpler and require fewer transistors than circuits designed with conventional structuring. As an introduction to the issue, let us first consider the simple D-Latch circuit shown in figure. The gate level representation of the D-Latch is simply obtained by modifying the clocked NOR-based SR latch circuit. Here the circuit has a single input D which is directly connected to the S input of the latch. The input variable D is also inverted and connected to the R input of the latch. The input variable D is also inverted and connected to the R input of the latch. It can be seen from the gate level schematic that the output Q assumes the value of the input D when the clock is active, that is for Ck equal to 1. When the clock signal goes to 0, the output will simply preserve its state. Thus, the Sk input acts as an enable signal which allows data to be accepted into the D-Latch. The D-Latch finds many applications in the digital circuit design, primarily for temporary storage of data or as a delay element. In the following, we will examine its simple CMOS implementation. Consider the circuit diagram given in figure, which shows a basic 2 inverter loop and 2 CMOS transmission gate TG switches. The TG at the input is activated by the Ck signal, whereas the TG in the inverter loop is activated by the inverse of the Ck signal. Ck dash, thus the input signal is accepted latched into the circuit when the clock is high, and this information is preserved as the state of the inverter loop when the clock is low. The operation of the CMOS D-Latch circuit can be better visualized by replacing the CMOS transmission gates with simple switches as shown in figure. A timing diagram accompanying this switch shows the time intervals during which the input and the output signal should be valid, unshaded. Here you can see the figure, gate level schematic and block diagram of the D-Latch. Figure CMOS implementation of the D-Latch version 1. Figure simplified schematic view of the corresponding timing diagram of the CMOS D-Latch circuit showing the setup time and the hold time. Note that the valid D input must be stable for a short time before setup time T setup and after hold time T hold. The negative clock transition during which the input switch opens and the loop switch closes. Once the inverter loop is completely once the inverter loop is completed by closing the loop switch, the output will preserve its valid level. In the D-Latch design, the requirements for setup time and hold time should be met carefully. Any violation of such specifications can cause metastability problems which lead to seemingly chaotic transient behavior and can result in an unpredictable state after the transitional period. The D-Latch shown in figure is not an edge-triggered storage element because the output changes according to the input. That is, the latch is transparent while the clock is high. The transparency property becomes the application of this D-Latch suitable for counters and some data storage implementations. Here you can see the figure CMOS implementation of the D-Latch version 2. And you can see the figure CMOS negative falling edge triggered master slave D flip-flop DFF. Figure shows a different version of the CMOS D-Latch. The circuit contains two tri-state inverters driven by the clock signal and its inverse. Although the circuit appears to be quite different from that shown in figure, the basic operation principle of the circuit is the same as that shown in figure. The first tri-state inverter acts as the input switch, accepting the input signal when the clock is high. At this time, the second tri-state inverter is at its high importance state, and the output Q is following the input signal when the clock goes low. The input buffer becomes inactive and the second tri-state inverter completes the two inverter loop which preserves its state until the next clock pulse. Finally, consider two-stage master-slave flip-flop circuit shown in figure, which is constructed by simply cascading two D-Latch circuits. The first stage master is driven by the clock signal, while the second stage slave is driven by the inverted clock signal. Thus, the master stage is positive level sensitive while the slave stage is negative level sensitive. When the clock is high, the master stage follows the D input while the slave stage holds the previous value. When the clock changes from logic 1 to logic 0, the master latch ceases to sample the input and stores the D value at the same time of the clock transition. At the same time, the slave latch becomes transparent, passing the stored master value QM to the output of the slave stage QS. The input cannot affect the output because the master stage is disconnected from the D input. When the clock changes again from logic 0 to from logic 0 to 1, the slave latch looks in the master latch output, and the master stage starts sampling the input again. Thus, this circuit is a negative edge trigger D flip-flop by virtue of the fact that it samples the input at the falling edge of the clock pulse. Figure shows the stimulated input and output waveform of the CMOS negative edge trigger D type flip-flop. The output of the master stage latches the applied input D when the clock signal is 1, and the output of the slave stage becomes valid when the clock signal drops to 0. Thus, the D-type flip-flop DFF essentially samples the input at every falling edge of the clock pulse. It should be emphasized that the operation of the DFF circuit can be seriously affected if the master stage experiences a setup time validation. This situation is illustrated in figure, where the input D switches from 0 to 1 immediately before the clock transition occurs. Setup time violation. As a result, the master stage fails. Figure shows the stimulated input and output waveforms of the CMOS DFF circuit in figure. In this figure, simulated waveforms of the DFF circuit showing a setup time violation for the master stage input at 10 nanoseconds. The output of the master stage fails to settle at the correct level. Layout of the CMOS DFF shown in figure. To latch the correct value, the slave stage produces an erroneous output. The relative timing of the input and clock signals are carefully synchronized to avoid such situations. The layout of the CMOS DFF circuit is given in figure. Another implementation of edge trigger D flip-flop is shown in figure, which consists of 6 NAND 3 gates. This D flip-flop is positive edge triggered as illustrated in waveform chart in figure. Initially, all the signal values except for figure NAND based positive edge trigger D flip-flop circuit. Figure timing diagram of the positive edge trigger D flip-flop. SR0, that is SR CK D equal to 1 0 0 0 and Q equals 0. In the second phase, both D and R switch to 1, that is SR CK D equal to 1 0 1 1, but no change in Q occurs and the Q value remains at 0. However, in the third phase, if CK goes too high, that is SR CK D is equals to 1 1 1, the output of gate 2 switches to 0, which in turn sets the output of the last stage SR latch to 1. Thus, the output of this D flip-flop switches to 1 at the positive going edge of the clock signal CK. However, as can be observed in the ninth phase of the waveform diagram chart, the Q output is not affected by the negative going edge of CK nor by other signal changes. Thank you.